Hello and welcome to Lesson 8.1. Today we're going to look at zero and negative exponents. When dealing with exponents, zeros and negative exponents are kind of like a special property. If you notice the first property, it says 0 as an exponent for every non-zero number a to the power of 0 equals 1. And if you look at the examples here, I have 5 to the power of 0 equals 1, a negative 2 to the power of 0 equals 1, a decimal of 1.02 to the power of 0 will always equal 1. A fraction of 1/3 raised to the power of 0 equals 1. Any number that you raise to the power of 0 will always equal 1. Please do not forget that. That is one of probably the most common mistakes. You just have to remember that anything raised to the power of 0 is always 1. Now for negative exponents, okay, I like to think of a negative exponent as a way to tell you that it's in the wrong spot, okay, or that power is in the wrong spot. So if you look at some examples, if I have 6 to the negative 4th, that's really written as, we could rewrite that as 6 over 1 to the negative 4th. So that negative 4 is telling me that the power of 6 to the 4th is in the wrong spot, and that 6 to the 4th should actually go to the denominator instead of being in the numerator, as you can see right here. Likewise, if I have negative 8 raised to the power of negative 1, that's really negative 8 over 1, and that tells me then, again, because of the negative exponent here, that needs to move down to the denominator. So then I would end up with 1 over a negative 8 to the first power. Now this also works in the sense that if I have 1 divided by, let's say, 3 to the negative 2nd, okay, I can think of that negative exponent saying, hey, I don't belong in the denominator, I actually belong in the numerator. So this here is really going to become 3 to the power of 2nd, and you could write it over 1 if you wanted to. So a negative exponent tells you that if it's in the numerator and it has a negative exponent, that it really belongs in the denominator. And if it's in the denominator with a negative exponent, it really belongs in the numerator. Whenever you move it from the numerator or the denominator, once you move it to its new location, it no longer has a negative sign. And we'll take a look at a few examples here. But before we do that, I want to reiterate, any non-zero number that's raised to the power of 0 is always going to equal 1. Please do not forget that. So with example 1, part A, we have 3 to the negative 4th. You could really rewrite that as 3 over 1. So what this tells me then is I need to move that 3 to the 4th power over, or out of the numerator and into the denominator. So that's going to give me 1 over 3 to the positive 4th, because again, once I move that from the numerator to the denominator, I have to get rid of that negative. And then I can now simplify. 3 to the 4th power is actually 81. So this is going to simplify down to 1 divided by 81. Part B, this is a negative number raised to the power of 0. This is always going to turn into the number 1. Part C, I have negative 4 raised to the negative 3rd power. Remember, that's really over 1. So that tells me that I need to get that power out of the numerator and into the denominator. So that really turns into 1 divided by 4 to the, that's a negative 4 to the 3rd power. So negative 4 to the positive 3rd power. And when I simplify, I have 1 divided by negative 4 to the 3rd power is actually going to give me a negative 64. So I'll keep the 64 down there, and I'm going to bring the negative outside. For part D, this is 7 raised to the negative 1st. So I can really rewrite that as 1 divided by 7 to the 1st, which will simplify just to 1/7. And then finally, I have a negative, this could really be written as a negative 3 to the negative 2nd power. So when I simplify that, I really have a negative, and then 3 to the negative 2nd is really 1 divided by 3 squared. And then I can simplify that. My negative stays outside. 1 divided by 3 squared is really 1/9. And to simplify the whole thing, I end up with a negative 1/9. And this would be my final answer. Now for example 2, we're going to simplify each expression. One thing I want to point out when we're dealing with exponents is you only move the component that has a negative exponent. So if I look at part A, this is really 11 times m to the negative fifth. So the 11 does not have any exponent, and really that's all in the numerator. So my 11 can stay in the numerator. My power of m to the negative fifth, that's in the numerator. Because it has a negative exponent, it tells me that it really belongs in the denominator, so I'm going to rewrite this as 11 divided by m to the fifth power. Likewise, for part B, I really have 7 times s to the negative fourth times t squared. This would all be written over 1. So what I'm going to do here is I'm just going to go step by step, and 7 has no negative exponents, so that will stay in the numerator. S to the negative fourth, the negative 4 tells me that the s actually belongs to the bottom or to the denominator, so this becomes s to the positive fourth, and then I have t squared, which has a positive exponent, so that is going to stay in the numerator. Likewise, for part C, 2 is going to be left where that is because that's in the numerator, doesn't have a negative exponent. Now in this case, my denominator has a negative exponent, so that tells me that that really has to move to the numerator. So I really end up with 2a to the third power. And for part D, I have negative, or n to the negative fifth. So that negative exponent tells me that it needs to move out of the numerator into the denominator. And if I have nothing left in the numerator, then I'm just going to replace it with a 1. So this would be 1 divided by v squared n to the fifth. And as you can see, things are going to get a little bit more complex here. So for part A, I have w is being raised to the power of 0. So anything raised to the power of 0 is always 1. So I really have n to the negative third power times 1. And because n to the negative third is really in the numerator, I can go ahead and rewrite this as 1 divided by n cubed. Now in this case, I know that n is really going to be negative 2 based on what I have here. So I really have 1 divided by a negative 2 to the third power. And a negative 2 to the third power is actually going to give me a negative 8. So I end up with a negative 1/8. Likewise, for part B, my n to the negative first really tells me that I'm going to have 1 divided by w squared times n to the first. And when I plug in my values for n and w, I end up with 1 divided by 5 squared times a negative 2 to the first. So this is going to give me 1 divided by 25 times a negative 2, or I end up with 1 divided by a negative 50. And then for part C, I notice right away that I have something raised to the power of 0, so that's going to turn into 1, and I end up with 1 divided by n to the fourth. So if I plug in my value of n, I really have a negative 2 raised to the power of 4. And please take note, I am plugging my negative numbers into parentheses because a negative 2 raised to the power of 4 is different than, let's see, so this right here is not equal to this right here. Okay, because in this case, I have negative 2 times negative 2 times negative 2 times negative 2. This case here is really like saying negative 1 times 2 to the fourth. So this is going to give me a negative answer. This will give me a positive. So it does matter. When I simplify here, I end up with 1 divided by 16. Now for part D, my last part, notice that I really have 1 divided by n times w to the negative second. So what this tells me is that w to the negative second, this part here is in the wrong spot and really belongs in the numerator. So this really gives me w squared divided by n, I'm going to plug in my values. So I have 5 squared divided by a negative 2, or I end up with 25 divided by negative 2, and you can go ahead and leave it like that. For example 4, it says a biologist is studying green peach aphids, like the one shown on the left, which I did leave the picture of, I apologize. In the lab, the population doubles every week, and it gives us the expression of 1,000 times 2 to the power of W. This models the initial population, which is 1,000 insects, after W weeks of growth. We want to evaluate the expression for W equals 0 and tell what the value of the expression represents. So ultimately what I have is that my population is equal to 1,000 times 2 to the power of 0. So if you remember, anything raised to the power of 0 is 1. So this really gives me 1,000 times 1, which is 1,000. Okay, this here is telling me what my initial population is. So this is the initial population at, and I'm going to put t equals 0 or when time equals 0. And that actually is told to you right here. For part B, it says evaluate the expression for when W equals a negative 3, then describe what the value of the expression represents in this situation. So here, we're looking at our population as being equal to 1,000 times 2 to the negative third power. So what this really means is I have 1,000 times 1 over 2 to the third, or 1,000 times 1/8, which is going to give me 125 when it's all said and done. Now, if you think about it, we were told that W represented the number of weeks. Okay, it says weeks of growth. So essentially what we're looking for when we have a negative value for W is that means what was our growth 3 weeks prior to this study began? Or how many aphids were there like 3 weeks ago? Example 5 is another example that deals with population. Okay, and it says a sample of bacteria triples each month. The expression is given by 5,400 times 3 to the power of m, models the population of 5,400 bacteria after m months of growth. We're going to evaluate the expression for when m is equal to negative 2 and when m equals 0, and then we're going to talk about what each situation represents. So when our population we're going to find our population for when m equals a negative 2. So I have 5,400 times 3 to the negative second. So this equals 5,400 times 1 divided by 3 squared. And if you remember, 3 squared is really 1 divided by 9. So if I take 5,400 and divide it by 1/9, I'm really left with 600 bacteria. So when m equals negative 2, okay, we have a negative exponent, and we know that m is the number of months of growth. So a negative 2 months of growth means that this is the amount of bacteria 2 months prior to the this study beginning. So we'll say prior to the study starting. Okay, for the second part of this, we are looking to see when what our population is when we have a value of m equals 0. Now remember, anything raised to the power of 0 is always 1. So this gives me a population of 5,400 times 1, which is equal to 5,400. So again, when the exponent is raised to a power of 0, this right here is telling us that when m equals 0, we have the initial amount, or our starting amount, of bacteria. Okay, and the starting amount would be like when this study started. Please let me know if you have any questions. Otherwise, I hope you guys have a great day, and we will see you in class.